Hello everyone, my name is Xiaojiang. Today I'm gonna present our work on benchmarking the GPU performance characteristics of graph foundation models. Our central question is when graph foundation models run on a GPU, what actually happens at the hardware level, and where do the bottlenecks come from? Before we dive in, let me briefly explain what a graph foundation model is. You're probably familiar with some foundation models like GPT or BERT. Those models are pre-trained at a scale and then adapted to a wide range of downstream tasks. The goal of a graph foundation model is also to train a general purpose model that can generalize across graphs and tasks. For example, there are some applications of graph foundation models. The Kumo AI, they have relationship foundation models, and for Google, they have Google Knowledge Graph, and for Pinterest, they have Biparty Graph. Those are all graph foundation models. So there are three graph foundation model paradigm we studied. First is the LLM-based GFMs. It's represented by graph LLM, which use dBERT as its backbone. The second one is GNN-based unified modeling, represented by One for All. It's a general-purpose graph learning framework. The second one is GN plus LM hybrid, represented by Graph Translator, which supports fully inductive learning. Those three models cover different backbone types, adaptation mechanisms, and graph generation strategies, making our finding broadly representative. All those three paradigms share a common challenge: increased model complexity, irregular data access, and high memory and computation demands. On the background side, GFMs are pre-trained on massive multiple graph cover and then adapted to heterogeneous downstream tasks. The gap is virtually all previous work focused on predictive accuracy, system-level GPU behavior is poorly understood, and graph workloads are already difficult for GPUs because sparse connectivity and the data-dependent control flow, they create inherent irregularity. Our work fills this gap. We selected three representative GFMs, profiled them with using NVIDIA Insights tools on an L40S GPU and systematically identified these system-level bottlenecks. For our methodology for model coverage, we profile different exclusion stages for each model: pre-training and training for graph LLM and OFA, stage 1, 2 for graph translator. Our execution pipeline flow from graph data through pre-training, adaptation, and inference. Importantly, we profile only steady-state execution. We exclude initialization and data loading so that the measurements reflect recurrent model computation. For hardware and tools, we use NVIDIA L40S GPU CUDA 20.4 and PyTorch 2.7, and Set Compute gives us kernel-level hardware statistics, and Nset Systems gives us timeline-level execution traces. Our analysis is two-level. We first correlate time, memory traffic, and utilization at the stage level, and dive into kernel level operators, compute adaptation, and the lunch overhead. So based on the methodology, we formulate 3 research questions. First research question is, what factors limit GFM performance on GPUs? Is it memory bandwidth saturation, atomic contention, or something fundamentally different from traditional GN workloads? The second research question is, how do operator mix and kernel granularity affect GPU occupancy? What roles do element-wise operations, GMMs, and scatter-gather play in determining SM utilization? The third research question is, how large is hosted kernel lunch overhead across GFM execution stages? Is it a meaningful bottleneck, or does it vary between pre-train and graph-heavy stages? So here's our answer to research question 1, the relationship between hardware utilization and memory bandwidth. Look at the table. GRM's pre-train stage achieves around 80% web activity, which is very healthy. But most other stages are much lower. OFA training is only 20%, and GT stage 2 drops to 13%. The critical observation is those low utilization stages also has very low memory traffic. This is telling if GPU utilization was low because our memory bus was saturated, we expected for high memory traffic, but we see very low utilization and low traffic, then the GPU is not waiting for the data. So our first finding is GFM pipeline exhibit low GPU utilization even under negligible DRAM traffic. Train and adaptation stages show web activity below 21% despite minimal memory pressure. Consistency with latency bound, not bandwidth bound execution. So now there's this question 2, how operator composition affects GPU occupancy. Look at the kernel breakdown. GRM pre-train has some GMM around 8.9%, and the average kernel time of 88.69 ms. Relatively efficient, but OFA train average only 7.29 ms per kernel, and GT stage 2 averages just 5 ms. The graph translator stage comparison is especially striking. Stage 2 launches over 50,000 element-wise kernels, each lasting only 3 to 8 ms. Even though GMM kernels are present, their benefit is diluted by constraint interleaving with those short-living kernels. The GPU keeps alternating between very short and longer kernels, so SM occupancy can never be sustained at a high level. Then we got our finding 2. GFM exclusion is dominated by thousands of fine-grained element-wise operations that prevent sustained SM occupancy. Even when GMM is present, its benefit is undermined by fragmented execution. Research question 3 gives us the most striking result. Hosted kernel lunch overhead. Look at the GRM training stage. The average lunch time is around 179 ms, but the kernel itself only takes 5 ms. Lunch overhead accounts for 97% of the total execution time. The GPU is spending virtually all its time waiting for CPU to issue next kernel, not actually computing. Other stages are also severe. OFA pre-train at 61%, OFA train at 56%, GT stage at 42 to 48%. The only well amortized case is GRM pre-train at 13% because transformer GMM kernels are large enough to absorb the launch cost. So we got our finding 3. Launch overhead accounts for 42 to 97% of execution time in graph-heavy stage. Its severity is tightly linked to the kernel granularity, and it directly explains the utilization gap we saw in research question 1. Now let's tie together all the 3 findings and compare GFMs to traditional GNNs. The root cause is tensor size mismatching. Transform matrix multiplications use large regular tensors that fully utilize tensor cores. Graph operations produce small irregular tensors that cannot fill the GPU. GFMs interleave, both creating persistent fragmentation. The comparison to traditional GNNs is revealing. Traditional GNNs are primarily bottlenecked by memory bandwidth and atomic contention. For GFMs, memory bandwidth is essentially a non-issue, and the atomics are minor. Instead, kernel fragmentation and launch overhead, negligible for traditional GNNs, become the dominant bottlenecks. The implication is important. Existing GNNs targeted optimizations like GNN Weather, TRP GNN, and Neural GNN, they address a different bottleneck for GFMs. The state-aware and structure-aware strategies are what actually needed. So let me wrap up with our 3 findings, contributions, and future directions. The first finding is now bandwidth bounded, and the second finding is kernel fragment dominance. The third finding is launch overhead is very high, it can be up to 97%. Our contribution is that this is our first systematic GPU performance study spanning all the major GFM paradigms. We provide fine-grained bottleneck across in training, adaptation, and inference, and we also show that GFM bottlenecks are fundamentally different from traditional GNN systems. For future work, kernel fusion to merge element-wise normalization and GFM operations, stage-aware optimization with different strategies for pre-training and graph-heavy stages, and structure-aware scheduling to handle dense or sparse pattern transition at runtime. In one sentence, GFM performance is constrained by exclusion, structure, efficiency, non-memory bandwidth, and this demands a fundamentally new approach to GPU optimization. Thank you for listening. Please feel free to ask any questions.